encode these numbers into the output of a quantum circuit amplitude. Okay, so if you could evaluate these quantum circuit amplitudes, you can compute these delta C's, which means you get to solve gap complete problems. Okay, so it can be shown that actually, in order to do this construction, you need a universal set of gates, the way that they did it. It turns out that using arguments based on post-selection, you can actually take away this universal gate set requirement. And so that means that you can, Alex and Scott showed that using these sort of tricks, you can show that the, how do I put it, the output probabilities of a linear optical circuit can be gap complete. Likewise, we've shown that IQP circuits, the sort of class circuits we're talking about, can also have gap complete output probabilities. Okay, so the idea is then to come up with an algorithm in BPP to the NP, which might be able to get a multiplicative approximation to these output probabilities. Okay, so let's give you a rough idea of how you can do that. All right, so say we want to know some particular output probability from your quantum circuit. Say the probability of getting the all zero state out. Okay, so you can write down your quantum circuit, and you want to get P of 0 out. So you write that circuit, and you send that circuit description to whatever device it is that is going to be trying to implement that circuit. So it could be a quantum computer, or it could be a classical computer trying to simulate that circuit. And you're going to have a guarantee that this device can simulate the circuit to within some constant additive error bound. Okay, so you send the circuit over, it implements it, spits out a bunch of ones and zeros, which you get to analyze. And you live in a world where you have a BPP to the NP machine at your disposal. Okay, at this point in the circuit, you can just use Markov's inequality to get a bound between the output probability that this thing gives for any given x and the output probability that you actually wanted. Okay, and there's nothing magical going on here. We can just write that down using Markov's inequality. Now, you're going to feed this into this device, and you're going to apply the Stockmeyer counting algorithm to try and get an approximation to this P of 0 thing that you wanted in the first place. Well, you do that, and you know that the Stockmeyer counting algorithm gives you a 1 over poly multiplicative approximation. You do a bit of triangle inequality and stuff, and then you get an answer that looks like this. So you get a bound between A and a randomly chosen output probability, which is bad because it means that we don't get a bound between A and P of 0. So, that's a bit sad. The really good idea, which one way, how do I put this? This can be overcome by randomly choosing your input instances to this problem. Okay, so if instead instead of starting with a fixed circuit, we instead now start with a circuit where we say randomly bit flip just before we do a whole bunch of random bit flips before we do the final measurement outcomes. Okay, and then we ask the question, what is the probability of measuring all zero at the output? Go through the same procedure. In a sense, this instance is hidden, or the instance we cared about is hidden by in the description of the circuit because it's an IQP circuit. It's not so important. But the point is that you run this analysis, you do Stockmeyer counting, and you find that you get a bound on the probability of measuring the all zero state out. Okay, so we've interchanged the probability of the random choice over the outputs, which we had in the previous slide, with a random choice over the inputs to your circuit. And the same analysis then gives us a bound on gives us a bound that Stockmeyer's algorithm computes a given output probability for a randomly chosen circuit as opposed to a randomly chosen output for a given quantum circuit. Okay, so that's great, but this is still not really what we want. What we want is a multiplicative error bound on this output probability, okay? Because as I was saying before, if you have multiplicative error bounds for gap P hard problems, gap P hard problems are still gap P hard, okay? Well, it turns out that, well, and one way you can see that this will always happen if p dash of 0 is lower bounded by 2 to the minus n. Okay, and that you can just show with some straight algebra. So what we want to show is if that something, you want to guarantee this, and also show that if this thing is sharp p hard over the random choice we've made for the circuit class at the beginning, then the polynomial hierarchy would collapse if there was a classical simulation of these circuits. Okay, so now we're sort of going back to why we were talking about the original circuits I was talking about at the beginning of the talk. Both these classes of circuits satisfy this anti-concentration condition. Okay? So if you were to randomly choose from the Ising model, it turns out that, as I said, you can represent the Ising model by Hamiltonian. You can write the partition function for that Hamiltonian, or the complex temperature partition function of that Hamiltonian like this. Okay? And the output probabilities from these sort of circuits are always proportional to these complex temperature Ising model partition functions. This class of functions has the property that they stay sharp p hard under multiplicative approximations. We show that in our paper, and also was shown recently by Goldberg and Guo. And Fujimura showed something which is kind of equivalent, but not quite that statement. Importantly, they also have the property that you can lower bound these output probabilities by 2 to the n, which means that they anti-concentrate over this random choice of circuits. Okay? So, given these random choices, the ones I discussed earlier, then this IQP sampling procedure outputs some A which approximates these partition functions to within a constant multiplicative error bound over these random choices. Now, we need to make a conjecture here because we actually don't know the complexity of getting this kind of we don't know the average case complexity of this level of approximation for this kind of problem. Okay. Where do we get our other conjecture from our other circuit class? Likewise, as I said before, these circuits sample from the outputs of Fourier transforms of these degree 3 polynomials. It's been known for a long time that, and in the case when the input is 0 and the output is 0, this can be shown to be the output probability is equal to the gap of a degree 3 polynomial over F2. This problem is basically the definition of a gap p-hard problem. And so the IQP sampling procedure for a random choice over these circuits gives us an approximation to the normalized gap of degree 3 polynomials to within a constant multiplicative error bound. And as I've said, this parameter choice leads to sharp p hardness for these problems. However, what we actually need to know in order to show that if quantum computers could be simulated, then the polynomial hierarchy collapses, is that this remains gap p hard in the average case, okay? Or sharp p hard on the average case. Okay, so let's just compare what we've done with what happens in the Aronson and Arkhipov paper for linear optics. So these are a bunch of ingredients which are kind of necessary to their argument. That amplitudes are sharp p hard to precisely compute, probabilities are sharp p hard to multiplicatively approximate, okay? That we have one of these sort of sampling type procedures, okay? That's using the language of hiding matrices inside other matrices. That's kind of this process of making a random choice and doing it in such a way, actually, it turns out you need to do it in such a way that you can hide your choice over random circuits from your sampling device. That's just a technical requirement. It's easily true in our case. It's a bit more work in the linear optical case to prove it, but you can. And then they have to make these two conjectures, which is that these classes of permanent, which can be related to the linear optical systems that they care about, actually anti-concentrates. And that's basically proving that this whole sampling procedure actually guarantees you a good approximation to the probability, output probability of a circuit that you cared about. In our case, this turned out to be easy to compute. It's a lot more work in linear optics to prove this. And so that problem is still open. Likewise, they had to conjecture about the average case complexity of precisely this class of permanents. All right, like I said, so why do we choose particularly these circuit classes and not, say, some other class of IQP circuits or just some other class of quantum circuits and try and run this sort of argument? Well, it turns out that the commuting properties of these sort of circuits, the fact that, like, we have all these mutually commuting gates in the circuit, makes it easier to do computations on the output probability distributions of these circuits. The actual total, the proof of the anticoncentration follows from the Pauli-Zygmund inequality and a lot of counting of roots of unity, as you can probably imagine. There may be other choices of IQP circuit that allow for this sort of anticoncentration, for instance. So computing these things isn't so hard in the case of IQP circuits, but you actually need quite a lot of depth to the circuit. That's kind of something we notice with these techniques. So you need sort of still do something like, well, I'm not too sure what a lower bound is, but I mean, it worked in the case where you do n squared gates. I'm not so sure it works, say, in the case of autolog n gates. All right, so where we get a bit of difference between, or maybe our argument falls down a bit compared to linear optics, is we don't know an awful lot about the average case complexity of these Ising model problems. And you can there's a lot of evidence sort of for and against our conjecture. So gap P complete problems are always randomly self-reducible, so they're always sharp P hard on average, but for a given choice of average. It may not be over the probability distributions that we care about, okay? So that's kind of the challenge, is proving this. Now, in our favor, the complex Ising model is kind of sharp P hard for most parameter choices. So this has been well studied and kind of well understood. And similarly, the sharp P hardness of the Ising model follows, sort of random-like cases, follows a lot from Baharoni's work on spin glasses. But he doesn't really prove results about average case complexity, but rather worst case complexity for those problems. Against our argument is that not quite against, but in the case of linear optics, you can actually prove that for the Gaussian permanent estimation problem, is sharp P hard on average in the exact case. But when you want to weaken this to an approximate case, this doesn't really work. So generally, these sort of proof techniques use linear interpolation, and that linear interpolation won't give you tight enough bounds to prove the sort of results that are needed for this to ultimately be true. Okay, so something new has to be invented in this case. You really need to do something a bit different from what the standard tricks will give you. All right, so you can also ask the question, what about completely other circuit classes? And Bill Pfefferman and Chris Humans, and Bill's in the audience, showed that for universal circuits, you can actually come up with a similar sort of argument. In their case, it's really great because they actually prove the equivalent of the random self-reducibility conjecture, so they sort of prove average case hardness for the right things. Unfortunately, the anti-concentration conjecture gets a whole lot harder in their case. And so we don't really know, and talking to Bill, it's not really clear what we can do there. So a really interesting question is, can the commuting two-local gate results of Boulon, Manchiska, and Zhang be extended to show families of circuits and corresponding conjectures that also imply quantum supremacy? So maybe they will allow us to broaden our results beyond the specific gate sets that we have here. And like I said earlier, are there any other circuits of, say, lower depth or simpler classes of IQP circuits that are also quantum supreme? All right, so my concluding slide, obviously prove the conjectures, right? That's the big question. Can we actually prove the conjectures? If we can, we've now got a really, really strong argument that quantum computers can't be classically simulated, and we can kind of move on. The other point is that, we should also find a convincing argument for the verification of Boson and IQP sampling experiments. So the problem, which a lot of people raise all the time with this sort of argument, is that, say you have a 50-qubit system, it's going to be really hard to classically simulate that, but we're going to run our 50-qubit system, do our IQP sampling or Boson sampling procedure. What you're going to get out is a whole lot of random numbers, and you have to somehow verify that what you've done matches what you were supposed to do, okay? For large numbers of qubits, this is going to be hard. These problems are outside MP. That's the whole kind of point of the argument we're making. They don't have efficient verification procedures. So we need to find a way of convincing people that when you're building these circuits, you're actually building something which is vaguely, well, works, basically. And finally, yeah, we'd like to discover new quantum algorithms that somehow use the post-classicality of IQP or Boson sampling-like circuits. So, you know, sampling problems, the way I have to present them are just like we're doing random sampling on random things. We're not really doing algorithms. It would be nice to actually show that the quantum supremacy of these classes of circuits can actually be exploited to do something we care about. OK, thank you.
Great, thank you. Are there questions? We have time for a couple questions. In the corner.
Yeah, I was just wondering, so the IQP circuits that you talk about,
Yeah.
you know, you mentioned they're generally sort of involve long-range gates. And you said if you sort of parallelize them, you can sort of implement them with short-range gates.
Yes.
But can you elaborate on that a little bit more?
Sure. So I don't know if I said it very clearly, but what I wrote up on the slide was that if you have a universal set of gates, then you can get away with the long-range gates. So one way of doing that, obviously, just be using swap gates. All right. So you can just use swaps to like swap qubits around. In a 2D lattice, for instance, you can parallelize this process a lot. So if you're constrained to a line, this is not going to be a happy story. Like, you know, you have to do n squared gates. It's going to go up like n cubed because you might have to like, you know, qubit 1 has to qubit n. So you have to swap everything in between. And you can only do sort of one gate at a time. But if you have a lattice or sort of a high dimensional thing, you can parallelize this tons. So then it doesn't turn out to be too bad in terms of scaling.
People are probably anxious for lunch. Is there one more? Any other questions? Okay, maybe can you comment on, have you thought at all about quantum algorithms or applications of these IQP circuits?
Yes. For exactly the classes we're talking about, like where you have these Ising type circuits or these degree 3 polynomial type circuits, I don't know of any algorithms specifically, but for a broader class of these circuits where you have sort of Hadamard's, diagonals, Hadamard's, you can construct algorithms which identify properties of binary linear codes, which demonstrate some sort of, well, they look like they outperform classical algorithms for doing the same thing. There's a really closely related class of problems which Fahi's developed on approximate optimizations, or approximate optimization problems, which are not quite inside IQP, but like they're just outside. So, you know, you could write down these circuits as being like an Ising type interaction, but instead of having the single qubit terms being like commuting with the 2 qubit unitaries, they are like in the Z basis or something like that. And in that case, you can do things. And they're really close. So we're talking about like a depth, you know, constant depth difference between these two classes of circuits.
Great. Well, let's thank Michael one more time. We now